Here's the Lab 4 Arduino sketch. The highlights are putting the serial begin value to this specific number because this is what the VSA software requires. Also saying that the potentiometer is hooked up to pin A2 and the end scope is hooked up to pin A1. And also I decided to use microseconds throughout the sketch because it's more accurate than using millis or some other delay command. Here are the screenshots for when f equals 75. When fs is 100 and 142, it experiences aliasing. There the frequency graphs do not peak at 75. And for when fs is 200 and 500, they do not experience aliasing. That's at 75. And so is this one. Here are the results when f equals 100. For when fs is 100 and 142, they do experience aliasing. The peaks on these frequency graphs are not at 100. However, when fs is 200 and 500, there's no aliasing, as they both peak at 100. Here are the results for when f equals 215. Here, there's aliasing for when fs is 100, 142, and 200. None of these peaks are at 215 hertz. However, on the 500 fs, there is a peak at 215, meaning there's no aliasing, only in this one. Now, when f equals 300, aliasing occurs in all of the fs values. Here's when fs is 100, when fs is 142, when fs is 200, and when fs is 500, none of the peaks on the frequency chart are located at 300. Here are the results to the table. The values for the actual sampling rates, the sampling time, and the alias frequency experimental were all taken from the screenshots. The theoretical alias frequency is calculated down here. If the sampling frequency is greater than or equal to the Nyquist rate, then the alias frequency will just equal the input frequency f. You can see that for all of the ones that are colored in black. And then the ones that are red, those are the alias frequencies. And those are calculated as follows using the folding table. First, the ratio of f to fn is determined. And then depending on where it comes in the folding table, you perform this calculation. And it's an example of both ways, whether it's going right to left or left to right in the folding table. And then that decimal is then multiplied by fn, the Nyquist frequency, and then it will output the alias frequency. So here's another look at the table with all the values. Now to make the square wave, the circuit is hooked up to P1 to make the pulse, and so the potentiometer is set up for 500 hertz, and the pulse is going at 10 hertz. When I start the processing sketch, it will recreate the square, and in the frequency domain, it will start by going really high up at about at a 10 frequency, and then the voltage will teeter off as the frequency increases from there. Now for the triangle wave, the end scope circuit is hooked up to A1 again, and this option is the triangle wave. And then when I run the processing sketch, we get triangles as it recreates the initial wave. And on the frequency domain sketch, it seems like similar to the square wave, except it goes down even more sharply, and higher frequencies don't have any voltage at all.